Hi everyone, welcome back to the video where we are discussing about error detection techniques. So in this video, I'm going to discuss and demonstrate how the cyclic redundancy check method can be used to detect errors at the data link layer. CRC is one of the most prominent schemes that has been implemented at the data link layer for error control. Now, first things first. So CRC is one of the most powerful redundancy checking technique used primarily at the data link layer. Here, for a given m-bit data word, the sender generates a r-bit redundancy, which we call it as a FCS, which stands for frame check sequence. Okay, we call it as a FCS, frame check sequence, and appends it at the end of the data unit, such that the resulting code word, which includes both your m bits of data and your r bits of FCS, is exactly divisible by a predetermined binary number and transmitted to the receiver. To understand this statement well, let me explain you this particular diagram. This is your original data that you want to send, irrespective of how many number of bits are there. This is your data. Now for this data, I want to implement CRC method for error detection. The first thing I'm going to do is, initially I have something called as a divisor, which is common. This divisor has a total of r plus 1 bits. Now, let me say that if, as an example sake, if my divisor contains 4 bits, and less than this, so if I remove 1 from this 4, which I will get 3, I will append 3 zeros to my data and perform modulo 1 division here. Okay, and then I will get the remainder once again as 3 bits, which I will append to my data and send to the receiver. Now let me give you one more better way of understanding. I have my initial data bits. Now if I am the sender, and this is my data, right? This is my data. It might be, let's say that 10 bits or 20 bits or 30 bits, any number of bits. Let us assume 10 bits. Now for this data to implement CRC, the first thing that I need is to decide upon the generator polynomial, or in this case, let us call it as divisor. Now that is also a binary number, and I should know how many bits of it are there. Let us assume if my generator polynomial is 5 bits. If my generator is 5 bits, then what I will do is, for this m bits plus 5 minus 1 gives me 4. I will put 4 zeros here, and I will perform a binary division with my generator polynomial. And with this, I will get a remainder of 4 bits. So whichever remainder I receive as 4 bits, I will remove these 4 zeros, append these 4 bits to my already 10 bits, and I will send a total of 14 bits to the receiver. Now let me show you. M is 10, first 3 zeros, okay, or let my example 4 zeros, r is equal to 4. So your divisor will be 5 bits, and a total of 10 plus 4, 14 bits will be sent to your receiver. Now what happens at the receiver side? The receiver will collect all these 14 bits, and it will simply perform the same division again with these 5 bits. I told you, even before this particular CRC starts, both the sender and receiver has to accept upon a common generator polynomial. That generator polynomial will be used at the receiver also. And I will once again verify the remainder. If I get a 0 remainder, I assume that the data has got no errors at all, and I will accept it, and I will pass it on to the upper layers. But if I get a non-zero remainder, then I will assume that the data contains errors, and I shall request the sender to retransmit my data again. This is the concept of cyclic redundancy check. Now you can ask me, sir, what is the cyclic? Why should I call it as cyclic redundancy? This is based on something called as cyclic codes. So cyclic codes are special linear codes with one extra property. That is, in a cyclic code, if one code word is cyclically shifted, that means it is rotated. Cyclically shifted means rotated. If it is rotated, the resultant is also another code word. Because CRC uses these cyclic codes to implement error detection, we call it as cyclic redundancy check. Okay, so for m-bit data word, the sender generates an R bit redundancy. We call it as the frame check sequence and appends it at the end of the data unit. At the receiver side, you do the same process again. At the receiver, the data unit received is again divided by the same binary number used at the sender. This is your binary number, or we call it as a divisor. If the remainder is 0, the data is assumed to be error-free and is accepted. And if the remainder is a non-zero, it is considered to contain errors and rejected. So if it is rejected, means the sender has to retransmit the data again. To put it to perspective, what we do is the CRC is actually based on polynomial arithmetic. In particular, computing the remainder of dividing one polynomial in GF of 2. This means that it is Galois field with 2 elements by another. So if you divide one polynomial with another with respect to the Galois field 2, then that is where we are actually doing in a cyclic redundancy check. A polynomial in GF of 2 is a polynomial in a single variable x. So you only have x whose coefficients are either 0 or 1. Okay. Now you can understand, sir, I don't understand much of this, but it is a very simple technique. The thing is, if you are performing a polynomial arithmetic in Galois field 2, addition and subtraction are done modulo 2. They are both the same as the exclusive OR operator. I hope you still remember the truth table of an exclusive OR, XOR operator. The same thing that we do when we want to do addition or subtraction. Now, for example, the CRC method treats the message as a polynomial in Galois GF of 2. What do you mean by this? Now, let us assume that the message is this 11001001. If for this to be written in polynomial format or in Galois field of 2 format, first count the number of bits. There are total of 8 bits, right? So the last one is x power 0 and the first one will be x power 7 because it is of x power 8. Now, if you have a 1 here, you write that particular polynomial or you write that particular position x power 7 plus you have another 1. So x power 6 plus there is a 0 here. So there is the coefficient of x power 5 is 0. So you do not write that particular coefficient or particular element. X power 4, once again 0. X cube, there is a 1 here. So x cube. For x square, it's a 0. For x, it's a 0. For x power 0, there is a 1. So plus 1. So x power 7 plus x power 6 plus 0 plus 0 plus x cube plus 0 plus 0 plus 1. This is how you write a message or a binary message in the format of a polynomial, or you represent a binary message in a polynomial format. This CRC usually treats the message and the generator polynomial in this particular way. Now, the sender and receiver agree on a certain fixed polynomial called the generator polynomial. I've been telling you the same binary divisor should be used at the receiver also. How do you do that? Now, there are some certain polynomials which are standardized for data communication. Towards the end of this video, I'll show you those polynomials, and that we call them as generator polynomials. The general 16-bit CRC used across the world for communications, which we also call it as CRC CCITT standard, uses the generator polynomial x power 16 plus x power 12 plus x power 5 plus 1. So this is the most commonly used 16-bit generator polynomial. So when I see x power 16 here, that means I will be adding 16 bits of redundancy, or in other words, 16 CRC bits. In other words, if I see a 16 here, whatever the degree of the first element, that many number of CRC bits will be added. So 16 CRC bits will be added to your data. So how do you calculate them? We will show with an example. Okay. Now, to compute an R bit checksum, the generator polynomial must be of degree R. So if I want to compute a 16-bit checksum, the degree of the polynomial must be 16. The sender appends R 0 bits. I just told you in the very first example itself, right? So appends R 0 bits to the m bit message and divides the resulting polynomial of degree m plus R minus 1 by the generator polynomial. This produces a remainder polynomial of degree R minus 1 or even less, some cases, or less. The remainder polynomial has R coefficients which are the checksum. The quotient polynomial is discarded. You are least bothered about the quotient part here. Now to put this into perspective and to understand better, let me take a small numerical example and then I will come back and I will tell you what is this. So first let on proceed with my example. Let the message be 110010. How is this represented using the polynomial? First, please count the number of bits. 1, 2, 3, 4, 5, 6. 6 bits. So the first element will be x power 5 because you have to consider from x power 0. So there is a 1 here, x power 5. There is another 1 here, plus x power 4. For x cube, it's a 0. For x square, it is a 0. For x, it is a 1 here. So x power 5 plus x power 4 plus x. This is your m of x, which is your message polynomial. It is also saying, assume the generator polynomial g of x used is x cube plus x square plus 1. Now, without looking this, can you write down how this is represented in binary? X cube, so 1. X square, 1. There is no x, so 0. X power 0 is 1. So this is what we get. This is a generator polynomial. Calculate the CRC for the message. Now, what did I tell you? In order to get the CRC, now how many bits of CRC do we get? The degree of the generator polynomial. The degree of the generator polynomial is 3 here. Or in another case, if there are 4 bits in the generator polynomial, you will get 3 bits as the CRC. So let us proceed on. Now add 3 zeros to your generator polynomial, to your message, and start dividing it by the generator polynomial. I'm writing it down here for you, sir, for easier explanation. So 1101. So sir, why did you add these 3 zeros, sir? Because there are 4 bits in your generator polynomial, I add 3 zeros here. If I am having a 7-bit generator polynomial, I will have how many I will put? 6 zeros here. So now let us start. The first thing you have to do is, when you start this division, this is all in modulo 2 and in Galois field. So what do? If there is a 1 here, just write down the divisor here, 1, 1, 0, 1, and cancel out the first element. So, and you perform exclusive OR, 1, 1, 0, 0, 0, 0, 0 and 1 is a 1, and bring down the next one, 1. Because it's a 0 here, put zeros here, 0, 0, 0, 0. Always try to cancel out the first element. Remove this. So 0, 1, 1. Bring down the next 0 here. Once again, it's a 0 here. So let me put 4 zeros here. Always try to cancel out the first element. Okay. So remove this. 1, 1, 0. Bring down the next 0. So because it's a 1 here, write down your divisor, 1, 1, 0, 1. Remove this, 0, 0, 1. Get this down. So because this is 0 here, write down simply 0. Okay, remove the first element, 0, 1, 0. Bring down the remaining 0. And once again, the first element 0, just put down 4 zeros. So 1, 0, 0. So how many bits are left now? 3 bits. So that your generator polynomial has got 4 bits. And how many check bits you got, or how many parity, how many CRC bits you got? 3 bits. Now, what you do is, the next step that you have to do, you calculated the checksum, you performed the division. In order to send this data to the receiver, what you will be sending is 1, 1, 0, 0, 1, 0. This is your m-bit data word. Now, what did I tell you about redundancy bits? 1, 0, 0. Append them at the end, 1, 0, 0, and then send this to the receiver. So I just put it in this form of a box, as I told you earlier. Let me change the color. So this is your data word, which consists of m bits. This is your redundancy, which consists of r bits, and this entire thing is your code word, which consists of m plus r bits. So in this case, my data word is 1, 2, 3, 4, 5, 6 bits, and I'm having a 3-bit redundancy. So m plus r is equal to 9. So these 9 bits are now sent to your receiver. Okay. So this is what we perform. Now I'm going back to read this particular sentence. Okay. So let me read it. To compute an r-bit checksum. So to compute an r-bit checksum, if you want a 3-bit checksum, let us assume the generator polynomial must be of degree r. That means your generator polynomial's first coefficient should be x cube at least. The sender appends r 0 bits. So add 3 0 bits to the m bit message and divides the resulting polynomial of degree m plus r minus 1 by the generator polynomial. That's what you just did. And this produces a remainder polynomial of degree r minus 1 or less. The remainder polynomial has r coefficients. You have it or not? Same thing. Which are the checksum? So you got in our example we got 1 0 0. Which are the checksum? So these 3 bits are now appended to your original message and then passed on to the receiver. Sir, what happened till now? So you just did some performance, or you performed some division. You got some 3 bits and you are saying that you added it to your data and I'm sending to the receiver. What is the purpose of all this? Why you did all these things? Now let me show you how the same calculation is done at the receiver side. The receiver, upon receiving all this data, it has now got 1 1 0 0 1 0 1 0 0. Okay, I told you that this generator polynomial is standard, which is once again used at the receiver. So the receiver, after receiving this entire data which you send, has to perform the same calculation again. Now let me show you. Let me do the same division again at the receiver. So 1 1 0 1, because it's a 1 here. Remove the first element. 0 0 1. Get this down. 1. So there is a 0 here. So 0 0 0 0. Remove the first element. 0 1 1. Get this down. 0. So because it's 0 here, 0 0 0 0. Remove the first element. So 1 1 0 1. Because it's a 1 here, write down your divisor. So remove the first element. 0 0. So 0. So even after this, you get a 0 here, and remove the first element, and 0 0 0 0. Even after this, you get a remainder of all zeros. So if this is the case, if there are no errors during transmission of this data, if the data being received as 1 1 0 0 1 0 1 0 0, which is the actual data sent by the sender, if this data is received at your destination without any errors, then you should get a 0 reminder, which you just got. So when you get this 0 reminder, which means, or which tells the receiver that your data has been received without any errors, and hence that the receiver will accept the data, removes these 3 redundant bits, and it will pass on the original data of 1 1 0 0 1 0 to the upper layers. So it will remove this particular redundant bits, r bits, and it will only accept the m bits and it will send it. In case if there is some slight issue with the transmission, you will get a non-zero reminder here. When you get a non-zero reminder, your receiver will understand that there is an error during transmission and it will not accept the data. It will reject the data or discard the particular frame. The sender will now retransmit the data again. Now let me show you another example. So in this example, it is saying at the receiver, the code word is received as, a code word has been received at the receiver, and the receiver has to check whether the received code word contains any errors or not. There is also a generator polynomial which is given, which is used at the sender also. So let us do the same calculation. 1 0 1 0 1. So because it's a 1 here, 1 0 1 0 1. Remove the first element. 1 1 0 0. I'm just performing an exclusive OR here. Okay, so bring this 0 here. Once again, put because it's a 1 here. 1 0 1 0 1. Remove the first element. 1 1 0 1. Putting this thing down. Now once again it's a 1 here. 1 0 1 0 1. Now the first element. 1 1 1 1. Bring this one down. 1, because it's a 1 here. 1 0 1 0 1. What happens? Remove the first element. 1 0 1 0. Bring this 0 down here. What happens? Once again it's 1 1 0 1 0 1. Remove the first element. 1 0 0 0 1. Bring this one down. So 1 0 0 0 0 0, because it's a 0 here. Move the first element. 0 0 1 1. And bring this 0 here, because it's 0. I am writing all zeros here. Remove the first element. 0 1 1 0. Bring the 1 down here. So 1 0 1 0 1. So, oh, my mistake. Sorry, because it's 0. I have to write all zeros. My mistake. I'm sorry. 0 0. So remove the first element. 1 1 0 1. Bring this last element here down. Excuse me, 1, because it's a 1 here. Add down your divisor. 1 0 1 0 1. So this goes 1 1 1 0. This, your remainder that you got is 1 1 1 0. Because this is a non-zero remainder, you are to assume that this data has errors. The thing with CRC is, because it's an error detecting code, it will tell you whether there are any errors in the received code word or not. It will not tell you which bit positions have come in error. There is no way to identify. It is only going to tell you if there are any errors. It does not tell you how many errors are there, which bits are in error, or which type of error you got. Nothing of that sort. It will simply only tell you that there is this transmission has errors, and once you get a remainder as non-zero, the receiver will reject this data and it will send, and it will wait for the sender to retransmit the data again. Okay. Now, in both the examples, so you can tell me, sir, why did you stop at this point? If you see, once again, your generator polynomial is 5 bits and your remainder is 4 bits. In our earlier example also, this is 4 bits, your remainder is 3 bits. This is 4 bits and you get a remainder of 3 bits. That means whichever is here, if you write this down as I told you, x cube plus x square plus 1, the degree of the polynomial, whatever the degree of the polynomial of the generator polynomial is, x cube, you will get that many bits of your remainder. That many bits of CRC are actually appended to the data and then sent to the receiver. Okay. So we'll do some more examples maybe in the next video. So this is how you actually perform a CRC division in binary. In some cases, if you are interested to do in polynomial way also, these are the steps that you need to follow. So performing CRC calculation in polynomial arithmetic involves the following steps. At the sender side, first take m of x, you divide it or you multiply it with x power n, where n is the degree of the polynomial here. X power n is the degree of the polynomial. Then whichever data you got x power n into m power x, you divide it by the generator polynomial g of x. Ignore the quotient and keep the remainder c of x. Then you send the data in such a way that x power n into m of x plus c of x. Now to look this or to do this implementation, I have taken an example. Consider the m of x as 1 1 1 0 0 1 1 0. this should be written in polynomial format as, tell me how many bits are there? 1, 2, 3, 4, 5, 6, 7, 8. It is of 8 bits. It is of 8 bits. What will be the highest degree of the polynomial? X power 7. So x power 7 plus, there is a 1 here. So x power 6 position is there. Plus 1 here. X power 5 position is there. There is a 0 in x cube. There is a 0 in x power 4. And then there is a 0 in x cube. So there is no x power 4. There is no x cube. For x square, there is 1. I put it there. For x, there is a 1. I put it. For x power 0 position, there is a 0. So there is no x power 1. So this is my message polynomial m of x in polynomial arithmetic or in polynomial format. My generator polynomial is given as 1, 1, 0, 0, 1. Okay. What do you mean by this? Your generator polynomial has contains 5 bits. So the highest degree will be x power 4. So x power 4 plus x cube plus, there is no x square, there is no x here, and plus 1. The first step what it says is multiply m of x by x power n. For this example, this is m of x and x power n is x power 4 because this is the highest degree of your generator polynomial. So you multiply m of x into x power 4. What do you get? X power 7 into x power 4, x power 11 plus x power 4 into x power 6, x power 10 plus x power 4 into x power 5, x power 9 plus x power 4 into x square, x power 6 plus x power 4 into x 5. So this is the resultant of step 1. Step 1, what we just did now. Then what it is asking you, divide x power n into m of x by g of x. What is your g of x? X power 4 plus x cube plus 1. So you take this value, now m of x into x power n, and you divide it by g of x. How do you do that, sir? Like this. So this is a value which you just wrote, and you start your division. Once again, you map the first element. So x power 4, x power 11. So I need to multiply this with x power 7 first. So you multiply this x power 7 and write it down here. X power 11 plus x power 10 plus x power 7. So what you are getting here? This is gone because it's the two same elements, exclusive r. This is a 0. So this is gone. X power 10 is gone. So you write down the remaining ones. X power 9 plus x power 7 plus x power 6 plus x power 5. X power 9 and x power 4. So you now multiply this with x power 5. So x power 9 plus x power 8 plus x power 5. Once again, the common elements will be gone because of exclusive r. 2 ones or 2 zeros results in a 0. And x power 5 will also be gone. Write down the remainder ones. X power 8 plus x power 7 plus x power 6. So x power 8 here. So what you have to write? X power 4. You have to multiply the divisor with x power 4. So x power 8 plus, tell me, x power 7 plus x power 4. Once again, these two will be gone. And what you will be left with is x power 6 plus x power 4. So x power 6 and x power 4. What we should multiply with? X square. Okay, so x power 6 plus x power 5 plus x square. Once again, these two will be lost. So x power 5 plus x power 4 plus x square. Can we stop here? No. Why? Because the resultant remainder should be always less than the degree of your generator polynomial. So you multiply with x again. X power 5 plus x power 4 plus x. So these are the two common elements which are lost. So how much you will get? X square plus x. Is the degree of your remainder less than your generator polynomial? Yes. So you stop here. So now, what did you do, sir? What were we supposed to do in the next thing? In the next step, now you finish step 2. You divided x power n into m of x by g of x. What is your step 3? What is your step 3? x power n into m of x plus c of x, or you append this. This is your c of x. So what do you get, sir? The message polynomial that is to be transmitted from the sender is x power 11 plus x power 10 plus x power 9 plus x power 6 plus x power 5 plus, this is your x power n into m of n. What is the c of x? X square plus x. If you are interested, if you want to write this in binary format, tell me the binary format. If it is x power 11, how many bits will have? A total of 12 bits. So x power 11 is there, x power 10 is there, x power 9 is there, x power 8 not there, x power 7 not there, x power 6 is there, x power 5 is there. Is there x power 4? No. Is there an x cube? No. X square is there, x is there. Is there x power 0? No. So this is the data that is actually sent to the receiver. So your remainder is x power x. The CRC code bits are this. Now, if you calculate your normal binary division also, you'll get the same answer. Your m of x consists of how many bits? 8 bits. Your g of x consists of 5 bits, which leads to, if g of x is 5 bits, you will get a CRC of 4 bits. So ultimately, your code word will be consisting of 8 bits plus 4 bits, which is nothing but 12 bits. This is the same as this one. This is how you perform an arithmetic or polynomial arithmetic in a polynomial format also. You can do the same thing. You can convert this into binary. You can do the same calculations again and again, but you'll get the same answer. If you want, you can verify it with your own calculations. You ignore this question. Forget about this question part. You just keep the remainder. This is the most important one. Whichever remainder you get here, you have to append this to your original data word and then forward it to the receiver. At the receiver, you do the same calculations again, and if you get a 0 towards the end, that means that you have received the data without any errors. At the receiver part, it is for your, I'm leaving it for you guys. I hope you try to check whether my calculation is right or wrong. Okay. Now coming to this, sir, for CRC, what is the most important point? What is the critical point of operation? The most important thing is selection of a proper generator polynomial. If you don't select the generator polynomial properly, you cannot get the accurate results. So are there any particular things to be taken into consideration when deciding upon the generator polynomial? Yes, there are. The first thing is your generator polynomial must have at least 2 terms. At least there should be 2 terms. And the second most important thing is the coefficient of x power 0 must always be 1. That means that for any generator polynomial you select, there should be always +1 at the end. Because why I am saying +1? 1 stands for that the coefficient of x power 0 is 1 there. Okay. And it should not divide x power t plus 1 for t between 2 and n minus 1. What is the n here? N is the degree of the polynomial. To understand this properly, I'll saying that this is the generator polynomial x power 15 plus x power 14 plus 1. It cannot divide x power t plus 1 if t is less than 32,768. Sir, how did you get this number, sir? This 32,768 is nothing but, this is the degree of polynomial is 15, n is equal to 15, 2 power 15 is equal to 32,768. So a code word with 2 isolated errors up to this 32,768 bit parts can be bits apart can be detected by this generator. If we select such values, you can still detect 2 isolated errors which are up to 32,768 bits apart. And the last important property is your generator polynomial must have a factor of x plus 1. Okay, these are the 4 important points or the 4 important properties that a generator polynomial must have. Sir, what is the importance of CRC? CRC is a very effective error detection technique. Its performance can be summarized as follows. A CRC can detect all single bit errors, all double bit errors, any odd number of errors, and it can detect all burst errors of length less than the degree of the polynomial. What do you mean by this, sir? If I am using a 12-bit CRC or a 16-bit CRC, that means I'm adding 16 bits of redundancy. It is to ensure that any burst errors of length up to 16 bits are guaranteed to be detected by this particular method. Nowadays, we are using a 32-bit CRC. That means I'm appending 32 bits, 32 redundant bits for every data block. So which ensures me that a burst error of length less than or equal to 32 is always guaranteed to be detected. In addition, CRC detects most of the larger burst errors also with a high probability. That means if I am assuming that if I'm using a CRC 12, CRC 12 stands for I'm adding 12 redundant bits. It detects 99.97% of the errors with a length 12 or more. So even if it exceeds the burst length of the, or if the burst error length exceeds more than the number of redundancy bits that I added, still there is a very high probability for detection. That is the reason CRC is being widely used in LANs and WANs. And also another good advantage with CRC is that it can be implemented easily in the hardware cheaply. Because it can be easily implemented in the hardware, you can run it very, very fast. Okay. So before we close down, as I told you, these are the common CRC generator polynomials or standardizer generator polynomials that are used across the internet. So for CRC 8, we use this x power 8 plus x square plus x plus 1. This is the most common one which we use, CRC CC8ET, which is also a 16-bit CRC. This is a generator polynomial, x power 16 plus x power 12 plus x power 5 plus 1. This is the modern day CRC 32, which we are using it for Ethernet and 802.11. So x power 32 plus x power 26 plus x power 23 plus x power 22 plus x power 16 plus x power 12 plus x power 11 plus x power 10 plus x power 8 plus x power 7 plus x power 5 plus x power 4 plus x square plus x plus 1. So this is the fixed standardized generator polynomial to use, as I told you, because both the sender and receiver has to decide upon the same generator polynomial for implementation of CRC methods. Okay, so this is regarding the CRC methods. I'll plan to do more examples on CRC in my later videos. So till then, do take care. I hope you understood the CRC method. In the next video, I shall post the third remaining error detection method, which is nothing but your checksum. So thank you. Take care. Keep smiling.